For anything at all to happen in the universe, a force must act. For anything at all to happen in the universe, a force must act. We usually think of forces as moving things around, pulling this apple towards the ground or pushing a car up a hill. But forces also cause the sun to shine. They make the ice melt in your drink, and they cause a plant to emerge from a seed. Forces are the agents of change in the universe. To help us understand forces, thousands of scientists around the world have spent billions of pounds to build this machine. I'm standing 100 metres below the ground at CERN in Geneva, and this is the CMS detector, part of the largest and most complicated scientific experiment ever attempted. This experiment will give us deeper insight into the forces of nature than ever before. It's a long way from when Isaac Newton pondered the laws of gravity, but all part of the same story. We understand the world today in terms of four forces of nature: the strong and weak nuclear forces, electromagnetism and gravity. Now, gravity is perhaps the most familiar, but in fact it's by far the weakest of the four forces. So weak, in fact, that we can completely ignore its effects when we explore the subatomic world, at least with today's experiments. Besides the familiar but weak force of gravity, there are three other forces in this universe, each of which is vital for our existence. Now, it may not seem obvious, but the force that holds these bubbles together is the same force that allows this flame to burn: electromagnetism. It's the force that allows us to push and pull things, the force that allows us to see everything in the world around us, and the force that allows your TV set to work. Electromagnetism is the force that holds electrons in place around the atomic nucleus and holds the atoms and molecules in place in my body. It also causes electrons to repel each other. So even though the whole planet Earth is pulling the apple down to the ground, the apple stays firmly in my hand because the electrons in its surface are repelled by the electrons in my palm. I've used the word electromagnetism to describe a single force, but electricity and magnetism seem at first sight to be very different phenomena. The magnetism that makes this top levitate seems to have nothing in common with these electrical sparks. The Greeks knew that if you rubbed a piece of amber with fur, it would pick up feathers. They also knew that certain rocks attracted iron, but they had no idea that the two were related. For 2,000 years after the Greeks, we thought of electricity and magnetism as different phenomena. It wasn't until the 19th century that we discovered that they are, in fact, different manifestations of the same thing. Now, not a lot of people know this, but this silver box inside a traffic island in South London is in fact a monument to the man who set us on the road to that profound discovery, Michael Faraday. Inside here is an electrical substation that powers the Elephant and Castle tube station across the road. Now, the original idea was for this to be made of glass, so you could see the electrical transformers inside. And I think that would have been an even more fitting tribute to the genius that was Michael Faraday, because it's really true to say he was the founding father of the modern electrical world. Well, this is a more obvious monument to Michael Faraday outside the Institution of Engineering and Technology. And in here, they have some of Faraday's original notebooks. In this notebook, in Faraday's own elegant, if rather illegible handwriting, is a reference to his most famous discovery. It's here in the title: Convert magnetism into electricity. What Faraday had found is if you take a coil of wire and you move a magnet around inside it, you generate electricity. And it's machines like this that lie at the heart of every power station in the world. Faraday had shown that electricity and magnetism are intimately connected, but they weren't yet unified together into a single mathematical framework. It took a very different kind of physicist, James Clerk Maxwell, to see the true connection, and with it produce a revolution in our understanding of the universe that Einstein later described as the most profound and the most fruitful that physics has experienced since the time of Newton. This is the lecture theatre where Maxwell stood and taught electricity and magnetism to his students. I want to show you something about the beauty and predictive power of mathematics in the hands of Maxwell. These are almost Maxwell's equations. They predict everything that was measured by Faraday and his colleagues about electricity and magnetism throughout the 19th century. This, for example, is Faraday's law of electromagnetic induction. But Maxwell noticed that these equations are not mathematically consistent. He was forced to add an extra term, which is called Maxwell's displacement current. With this extra term, these equations can be recast into this form. These equations are equations for electromagnetic waves, waves of light. So, in one piece of genius, Maxwell had unified the forces of electricity and magnetism and made a profound connection between electromagnetism and light itself.
Maxwell's unification of electricity and magnetism is regarded as a great milestone in physics because it was the first time when two disparate pieces of physics, electricity and magnetism, both thought of as separate physical processes, were brought together under a single theory which incorporated the two together. And that's a very important thing in physics, to try and explain as much as you can as simply as possible.
The two forces of gravity and electromagnetism seem at first sight to be sufficient to explain everything we see or feel in our everyday world. But once we look inside the atom, it is immediately obvious that other forces must be at work in the universe.
By the mid-1930s, we knew that atoms are composed of electrons orbiting a nucleus of protons and neutrons. But there's a problem with this model because protons are positively charged. And so when they're close together, the electromagnetic repulsion should blow the nucleus apart. And that's not what happens, of course. There must be another force many times stronger than electromagnetism that glues the nucleus together. And that force is called the strong force.
The strong force is not only responsible for holding the nuclei of atoms together, and without that, every atom in the universe would just spontaneously explode. But it's also, and this is quite interesting, responsible for 98% of nuclear mass. That means 98% of my mass, your mass, the mass of the Sun, the mass of the Earth. And we don't quite know exactly how the strong force generates that mass. And so we want to study that in more detail.
The discovery of the strong force was a giant leap forward in our understanding of nature. But there were still phenomena that we couldn't explain. This is a PET scanner, and it's transformed the way we diagnose many diseases because it allows us to look inside the body and detect abnormalities in cellular activity. Machines like this were developed as a direct result of advances in particle physics. The P in PET stands for positron, an antimatter electron, identical in every way except it has opposite charge.
Positrons or electrons are emitted from the nucleus in radioactive beta decay.
And that's a process that baffled physicists throughout the early 1930s. And they knew that the nucleus was made up of protons and neutrons held together by the strong force. And they knew that beta radiation came out of the nucleus. They also knew that beta radiation was comprised of electrons. So where did the electrons come from? It was the Italian giant of science, Enrico Fermi, who finally solved the problem. In 1934, he proposed that there's a weak nuclear force that can convert protons into neutrons, or neutrons into protons, at the same time emitting electrons or positrons and neutrinos from the nucleus. Fermi had found the missing force that explained the inner workings of the atom.
He played a huge role in nuclear physics, and his weak force has played a huge role in us being here. In fact, it's critical that it's so weak because it controls the first stage of the sun's fusion cycle. Because it's weak, the sun only just keeps alight. It's been burning for 5 billion years already. If the weak force had been any more powerful, the sun would have burnt out before any of us got here.
Fermi's discovery of the weak force is not the end of the story. A few decades later, in the 1960s, scientists were able to bring together the weak force and electromagnetism into a single electro-weak force.
Is it possible that the strong force, and perhaps even gravity, could be unified with the electroweak force into a single superforce that ruled the universe in the first instant after the beginnings of time? Well, Maxwell's unification was inspired by experiments done on a single desktop. The experiments that may lead to the long yearned for theory of everything will be controlled from here, the nerve centre of the accelerator complex at CERN. Here, we'll recreate the conditions that were present in the universe less than a billionth of a second after the Big Bang. How do we recreate those extreme conditions here on Earth? You need one of these, the Large Hadron Collider. 27 kilometers in circumference. Inside here, we accelerate protons to 99.999999% the speed of light before bringing them into collision inside 4 giant detectors. And those detectors take pictures of the collisions 600 million times a second. These are the lengths we have to go to explore the forces of nature. Today we can describe everything that happens in terms of just 3 forces: the electroweak force, the strong force, and gravity. But some scientists dream of going even further and unifying those forces together into a single force, a theory of everything.
In the next programme, we'll reveal the missing piece of the particle puzzle.